Bonding a gas pipe to the surface doesn't transform it into a grounding electrode. The purpose of bonding, in this instance, is to connect the gas pipe to the surface's grounding electrode system. This connection ensures that the gas pipe maintains the same electrical potential as the grounding electrode system. This equalization of potential is crucial in preventing the accumulation of static electricity on the gas pipe, which could pose a hazard. Furthermore, the National Electrical Code, or NEC, mandates that the gas pipe be bonded to the surface to provide protection against the potentially devastating effects of lightning strikes. In the event of a lightning strike impacting the surface, the resulting surge of electrical current will seek a path of least resistance to ground. This path leads through the grounding electrode system and ultimately into the earth. If the gas pipe were not properly bonded to this grounding electrode system, the electrical current from the lightning strike could inadvertently flow through the gas pipe itself, potentially entering the building. This unintended path could result in a fire or even an explosion, highlighting the importance of proper bonding. However, the NEC explicitly prohibits the use of the gas pipe as a grounding electrode. This prohibition stems from concerns about the reliability of the gas pipe as an effective grounding path. The gas pipe may not have direct, consistent contact with the earth, and the connection between the gas pipe and the grounding electrode system itself might not be sufficiently robust or reliable to handle the substantial current from a lightning strike. This unreliability could compromise the grounding electrode system's ability to effectively dissipate the electrical current from a lightning strike into the earth. Consequently, this could elevate the risk of a fire or explosion within the building. To further elaborate, let's delve into the specific requirements and principles behind bonding and grounding. Grounding, in electrical terms, refers to the intentional connection of a conductive object to the earth, providing a low impedance path for fault current to return to the source. This path allows overcurrent protective devices, such as circuit breakers or fuses, to quickly trip and energize the circuit in the event of a fault, preventing electrical shock and minimizing the risk of fire. Bonding, on the other hand, involves connecting together all metal parts that are likely to become energized, creating an equipotential plane. This equipotential plane minimizes voltage differences between these metal parts, reducing the risk of electrical shock if someone comes into contact with two or more of them simultaneously. Now consider the gas pipe. It's a metallic object that runs throughout the building, and it's potentially exposed to electrical faults or lightning strikes. If the gas pipe were to become energized without being properly bonded, it could pose a significant shock hazard. That's why the NEC requires it to be bonded to the grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or the metal frame of the building if it's effectively grounded. These electrodes are connected together into the service equipment enclosure, providing a low impedance path to ground. By bonding the gas pipe to this system, you ensure that it's at the same electrical potential as the grounding electrode system, minimizing the risk of shock. However, using the gas pipe as a grounding electrode itself is problematic for several reasons. Firstly, the gas pipe may not have a sufficiently low impedance connection to the earth. The earth is not a perfect conductor, and the impedance of the grounding electrode is crucial in determining how effectively it can dissipate fault current. A high-impedance grounding electrode can impede the flow of fault current, delaying the tripping of overcurrent protective devices and increasing the risk of electrical shock. Secondly, the gas pipe is subject to corrosion and damage, which can compromise its electrical conductivity. Over time, corrosion can increase the impedance of the gas pipe, making it less effective as a grounding electrode. Damage to the gas pipe, such as breaks or cracks, can also interrupt the grounding path. Thirdly, the gas pipe is not under the exclusive control of the electrical system. It's part of the gas distribution system, and modifications or repairs to the gas pipe can affect its electrical grounding properties. This lack of control can make it difficult to ensure the reliability of the gas pipe as a grounding electrode. The NEC addresses these concerns by specifying the types of grounding electrodes that are permitted and by requiring them to be properly installed and maintained. Common grounding electrodes include ground rods, which are typically made of copper or copper-clad steel and driven into the earth to a specified depth. Ground plates are another option, providing a larger surface area for contact with the earth. The metal frame of the building can also be used as a grounding electrode if it meets certain requirements, such as being effectively grounded to the earth. In addition to specifying the types of grounding electrodes, the NEC also outlines the requirements for the grounding electrode conductor, which is the conductor that connects the grounding electrode to the service equipment enclosure. The grounding electrode conductor must be sized appropriately based on the size of the service entrance conductors, and it must be protected from physical damage. The NEC also requires that the grounding electrode system be tested periodically to ensure its effectiveness. This testing typically involves measuring the impedance of the grounding electrode to the earth. If the impedance is too high, it indicates a problem with the grounding electrode system, and corrective action must be taken. In summary, bonding the gas pipe to the grounding electrode system is essential for electrical safety, but using the gas pipe as a grounding electrode itself is prohibited due to concerns about its reliability and effectiveness. The NEC provides detailed requirements for grounding and bonding to ensure that electrical systems are properly protected from faults and lightning strikes. Let's further explore the specific code requirements and technical considerations related to gas pipe bonding. The NEC section 250.104b specifically addresses the bonding of other metal piping. It mandates the bonding of metal gas piping systems that are likely to become energized. This bonding is typically accomplished by connecting the gas pipe into the grounding electrode system, the service equipment enclosure, the grounded conductor, or the grounding electrode conductor. The size of the bonding conductor is determined by NEC Table 250.122, which is based on the size of the circuit that is likely to energize the piping. The bonding conductor must be installed in a manner that provides a low impedance path for fault current. This means that the conductor should be as short and straight as possible, and it should be securely connected to the gas piping and the grounding electrode system. The NEC also addresses the use of listed bonding clamps and connectors. These devices are designed to provide a reliable electrical connection between the bonding conductor and the gas piping. It is important to use listed devices to ensure that the connection is safe and effective. The code also prohibits the use of certain types of connectors, such as those that rely on mechanical pressure alone. These connectors are not considered to be reliable enough for bonding purposes. In addition to the NEC requirements, there may also be local codes or regulations that apply to gas pipe bonding. It's important to check with the local authority having jurisdiction to ensure that you are complying with all applicable requirements. Now let's consider some practical examples of gas pipe bonding. In a typical residential installation, the gas pipe is often bonded to the service equipment enclosure using a bonding jumper. The bonding jumper is typically a copper wire that is connected to the gas pipe using a bonding clamp and to the service equipment enclosure using a lug. In a commercial or industrial installation, the gas pipe may be bonded to the grounding electrode system using a grounding electrode conductor. The grounding electrode conductor is typically a larger copper wire that is connected to the gas pipe using a bonding clamp and to the grounding electrode using a lug. It's important to note that the bonding connection should be made as close as possible to the point where the gas pipe enters the building. This minimizes the length of the unbonded portion of the gas pipe and reduces the risk of shock. Also, it is recommended to inspect the bonding connection periodically to ensure that it's still in good condition. Corrosion or damage to the bonding connection can compromise its effectiveness. In the event of a lightning strike, the bonding conductor provides a path for the lightning current to flow to ground, reducing the risk of damage to the building and its contents. The bonding conductor should be sized appropriately to handle the expected lightning current. Finally, it's important to remember that gas pipe bonding is just one aspect of a comprehensive electrical safety plan. A comprehensive plan should also include proper grounding, overcurrent protection, and regular inspections to ensure that the electrical system is safe and reliable. Consider this scenario: our home has a gas meter outside with a steel gas pipe entering the building underground. Inside, the steel pipe runs to a gas furnace. The electrical service panel is located nearby. To properly bond the gas pipe, a bonding jumper, sized according to NEC Table 250.122 based on the service entrance conductor size, would be run from the gas pipe to the service equipment enclosure. This ensures that the gas pipe is at the same electrical potential as the grounding system. Now let's address the concern about lightning strikes in more detail. When lightning strikes a building, it introduces a massive surge of electrical current into the electrical system. This current will seek the path of least resistance to ground, and it will follow all available conductive paths. If the gas pipe is not properly bonded to the grounding electrode system, it could become a path for the lightning current. This could result in a dangerous voltage rise in the gas pipe, which could cause a flashover to other conductive objects, such as metal appliances or plumbing fixtures. A flashover can ignite flammable materials, causing a fire. Even if a fire doesn't occur, the lightning current can damage the gas pipe itself, causing leaks or ruptures. If the gas pipe is properly bonded to the grounding electrode system, the lightning current will be diverted to ground, minimizing the risk of damage and fire. The bonding conductor provides a low-impedance path for the lightning current to flow to ground, preventing a dangerous voltage rise on the gas pipe. The grounding electrode system, in turn, dissipates the lightning current into the earth. Remember, the grounding electrode system must be properly installed and maintained to be effective. The NEC provides detailed requirements for grounding electrode systems, including the types of grounding electrodes that are permitted, the size of the grounding electrode conductor, and the methods of installation. The grounding electrode system should also be tested periodically to ensure that it's functioning properly. In addition to bonding the gas pipe to the grounding electrode system, it's also important to protect the electrical system from lightning strikes using surge protective devices, or SPDs. SPD are designed to divert surge currents to ground, preventing them from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at subpanels throughout the building. In summary, bonding the gas pipe to the grounding electrode system is a crucial step in protecting the building from lightning strikes. The bonding conductor provides a low impedance path for the lightning current to flow to ground, preventing a dangerous voltage rise on the gas pipe. The grounding electrode system, in turn, dissipates the lightning current into the earth. SPD can also be used to protect the electrical system from lightning strikes. To reiterate the key differences between bonding and grounding, consider firstly, grounding provides a path for fault current to return to the source, allowing overcurrent protective devices to trip. Bonding creates an equipotential plane, minimizing voltage differences between metal parts. Secondly, grounding electrodes are connected to the earth, providing a low impedance path to ground. Bonding conductors connect metal parts together, ensuring that they are at the same electrical potential. Thirdly, the NEC specifies the types of grounding electrodes that are permitted and the requirements for their installation. The NEC requires that metal gas piping systems be bonded to the grounding electrode system. Ignoring bonding and grounding requirements can have serious consequences, including electrical shock, fire, and damage to equipment. It's important to follow the NEC and local codes to ensure that electrical systems are properly protected. For example, improper grounding can lead to electrical shock if a fault occurs in an appliance. Improper bonding can lead to electrical shock if someone comes into contact with two metal parts that are at different electrical potentials. Failure to protect the electrical system from lightning strikes can result in damage to electronic equipment and even a fire. The NEC is a comprehensive set of standards that covers all aspects of electrical safety. It's important to consult the NEC and local codes when designing, installing, or maintaining electrical systems. Ignoring these codes can have serious consequences. In conclusion, understanding the difference between bonding and grounding is essential for electrical safety. Bonding and grounding work together to protect people and property from electrical hazards. The NEC provides detailed requirements for bonding and grounding to ensure that electrical systems are properly protected.